Hey everyone, and welcome to The Explainer. Today, we are taking a fascinating statistical mystery, along with a viral stack exchange debate, and turning it all into a visual journey to understanding. We're going to take those dense concepts usually buried deep in math textbooks and bring them right to life for you. So, let's kick things off with a classic problem. How do you figure out who actually performed better when the tests are graded on completely different scales? It's a situation we see literally all the time, right? Whether you're in education, finance, science, how do you definitively declare a winner when the scoreboards don't even look the same?
Here is our roadmap for today's explainer. We'll start with comparing apples to oranges, then unpacking the z-score, getting into the standard deviation mystery, looking at Euclidean versus Manhattan, and finally, the final verdict.
All right, Section 1. Comparing apples to oranges, the test score dilemma.
Let's think about this. On the SAT, the average score is 1,500, and it has a standard deviation or a typical spread of 300. But on the ACT, the average is 21 with a spread of just 5. So, how in the world do we mathematically compare an 1,800 on the SAT to a 24 on the ACT? At first glance, they look entirely unrelated.
Well, it actually comes down to 3 incredibly simple steps that let us standardize these completely different scores into one dimensionless quantity. First, you just take the raw score and the population mean. Then, you find the difference by subtracting that mean from the raw score. And finally, you divide that result by the standard deviation. By doing this, the actual units of the test, they just completely cancel out.
Which brings us right to Section 2. Unpacking the z-score, the ultimate equalizer.
Okay, so what actually is a z-score? Basically, it's a way to normalize data, turning our raw test scores into this universal language of distance from the average. It doesn't matter if you're talking about test scores, or bone density, or even high-energy physics. A z-score tells you exactly how many standard deviations a specific data point sits away from the center of the pack. Positive means above average. Negative means below. Simple as that.
And this brilliantly illustrates our SAT versus ACT problem. Let's look at student A. They scored an 1,800 on the SAT. If we subtract the mean of 1,500, we get 300. Divide that by the standard deviation of 300, and student A gets a nice clean z-score of 1. They are exactly 1 standard deviation above the mean, which puts them at about the 84th percentile. Now student B scored a 24 on the ACT. Subtract the mean of 21, you get 3. Divide by the spread of 5, and student B has a z-score of 0.6, putting them in the 72nd percentile.
And boom, there's your answer. Because student A has the higher z-score, they unequivocally performed better compared to their peers. We've effectively solved our apples to oranges dilemma. By converting totally different scales into this single, standard score, we can make direct, fair comparisons across basically any normally distributed data sets.
Moving right along to Section 3, the standard deviation mystery, under the hood.
Now, calculating that z-score requires dividing by the standard deviation, right? But that actually hides a pretty fascinating quirk. To find standard deviation, you take the difference from the mean, you square it, you average those squares, and then you take the square root. But why? Honestly, if we just want to know how far data spreads from the mean, wouldn't taking the absolute value make way more sense? It would be so much simpler than squaring everything just to take the square root later on.
Believe it or not, this exact question sparked a massive debate among statisticians online. Over on the cross-validated stack exchange, this topic has been viewed hundreds of thousands of times. Data scientists have been passionately arguing the merits of both sides for nearly 16 years. So we're going to break down their best arguments right now.
Let's look at the absolute value method first, known as mean absolute deviation. It's actually a fantastic tool because it doesn't overly penalize a data set just for having 1 or 2 crazy outliers. Think about it. If a data point is 10 units away from the mean, its penalty is just 10. It's incredibly intuitive, it assigns equal weight to every error, and it's actually used all the time in model quality analysis under the name mean absolute error.
So, Section 4, Euclidean versus Manhattan, the geometry of stats. If absolute deviation is so great, why did the squared version become the global standard? Well, one brilliant expert from the source described standard deviation as calculating true Euclidean distance across space. It's like flying a straight line from point A to point B. Because it squares the differences, it naturally emphasizes larger extremes. Absolute deviation, on the other hand, is literally like driving a taxi through city blocks on a Manhattan grid. It measures the raw, step-by-step distance, treating all steps equally without shining a spotlight on the furthest points.
I absolutely love this quote from the forum. It visualizes the squared error as a vector in an n-dimensional space, essentially making standard deviation the Pythagorean theorem of statistics. Just like a squared plus b squared equals c squared, this geometrical approach allows mathematicians to easily add variances together when they're working with independent random variables.
So squaring isn't just some plot to torture students in math class, I promise. It holds a special kind of mathematical magic. The really vital point here is that a squared function is continuously differentiable. That means you can solve for the minimum error analytically using a simple closed-form equation to find the mean. If you use absolute values, the math just isn't smooth. You actually have to run a complex, time-consuming sorting algorithm just to find the median. Plus, squaring plays a completely unique foundational role in the central limit theorem.
But, and this is a big but, as one contributor pointed out, standard deviation is heavily tied to the assumption of a normal distribution. If you're measuring something like very small physical lengths with a ruler, you can never have a negative length. In cases like that, standard deviation might actually be the completely wrong tool for the job. It's a modeling choice. It is not an absolute law of the universe.
Which brings us to Section 5, the final verdict, choosing your model.
So what does all this theoretical math actually mean for you out in the real world? Well, because standard deviation squares the errors, it severely punishes outliers. And this exact fact led famous statistician and author Nassim Taleb to argue that we should completely retire standard deviation. He believes we should just use mean absolute deviation instead, because standard deviation exaggerates extremes in ways that just confuse everyday people and distorts our true understanding of normal spread.
So, I'm going to leave you with this final thought for today's explainer. The next time you see a z-score or a standard deviation in a news article or a research paper, I want you to ask yourself, is this actually an accurate picture of the typical spread, or are a few massive outliers secretly pulling the strings of that data? Which model actually fits your reality? Thanks so much for joining me on The Explainer, and keep questioning the numbers.